Welcome back. So we'll continue the discussion on this crosswind effect. So we have already shown some figure that crosswind works from left to right. So the effect of crosswind now will incorporate in these changes in terms of some perturbations and things like that. So what it's going from left to right. Now, since the blade is turning counterclockwise, looking upwind, the crosswind decreases the tangential wind speed when the blade is below the hub axis, and reversely increases it when above. Okay, so the change in tangential component of wind velocity of wind velocity, which is due to crosswind, is delta u t crosswind effect minus b naught cos psi. Now, when the blade is out of the plane of rotation by the flapping angle beta, there will be a component that there will be a component that decreases the perpendicular wind speed at blade. Delta up due to crosswind effect is minus v naught sine beta so using small angle approximation. Yaw error is predominantly a cosine cyclic disturbance affecting the tangential velocity. So this is cosine, this is sine. Okay, that's how this affects. Now we consider the yaw motion. So this also affects the blade velocities. I mean, apart from the gyroscopic moments and etc. Um, let's consider the blade straight up and yaw rate of q. So the blade will experience a velocity due to the yaw. So the blade will experience velocity due to the yaw. Now, uh, rotation of yaw mm, due to u rotation, which is q d yaw, d yaw, where d yaw is the distance from the axis of tower to the center of the rotor. Uh, d yaw is the distance from the axis of the tower to the center of the rotor. If the blade is inclined away, which is downwind from the plane of rotation, by the mapping angle beta, there will be increase in the effect. So not there. This will increase the effect by a factor, which is RQ sine beta. Now the effect is high or greatest when the blade is up or down, and non-existent when blade is horizontal. This effect is highest when blade is up or down and non-existence while horizontal. Now we use that small angle approximation using small angle approximation. So what we can write that d yaw beta plus r would be r beta d yaw would be d yaw. So what we have right delta ut due to yaw q d yaw cos psi delta up minus qr sin psi. These are similar to the crosswind terms, with the tangential term varying with the cos psi and the axial or perpendicular one varying with the sine side. So essentially, these are cosine and cyclic sine variation. Now we need to take into account uh, vertical wind shear. Okay, vertical wind shear. So that kind of that vertical wind shear means the essentially the boundary layer variation that would happen that would be there in the wind profile or free stream wind profile. There could be effect of roughness, terrain, and other effects. So uh, there is a gradient that exists as we go along the perpendicular direction from the surface, Earth surface. So those gradients are usually that creates that kind of a shear stress. These are called the shear stress due to wind velocity, and this is termed as wind shear, and that can be so. In a nutshell, this talks about the wind velocity variation in the perpendicular direction and the shear stress due to those velocity gradients and things like that. So we can model that. Let's say u1 by u2 as h1 by h2 to the power alpha, where alpha is power law exponent, and 1 and 2 correspond to different height. Okay. So also in simplified model, that is, in simplified aerodynamic model, it's assumed that the vertical wind shear is linear across the, so vertical wind shear is linear across the rotor, across the rotor. This is what we consider in the simplified. Now, so what will happen? We can write free stream wind at height h can be written that UH equals to U into 1 minus R by R K nu S cos psi, where H is H minus R when blade tip is down, and H is H plus R when blade tip is up. H is half height, K nu S is linear wind shear constant. Okay, and nu is, this stands for basically vertical shear. So now the center of the at the center of rotor and on the horizontal, So at the center of the rotor, UH is U. At the top with zero flapping, UH is U into 1 plus K nu S. And at the bottom, UH is U into 1 minus K nu CS. The incremental effect of vertical shear is predominantly on the perpendicular component of wind. Okay, so the tangential wind shear can be assumed to be zero. So that means the predominant effect of vertical wind shear is on perpendicular component. Hence delta ut nu s. So on tangential component it is assumed to be zero. Well, up nu s v minus u r by r k nu s cos psi. So similarly, one can include the horizontal wind shear as well. So we can consider the small angle approximation. So at different, then we can have a see a variation. Mm, mm, so this is talk about wind speed perturbations. So there could be axial flow, crosswind, yaw rate, vertical wind shear. So this is delta UP, this is delta UT. So axial flow, this is U, 1 minus A R beta dot, crosswind minus V naught beta sin psi minus Q R sin psi minus Q R by R K nu S cos psi. This is omega R minus V naught cos psi minus Q d cos psi, and this case 0. So obviously this using this small angle approximation. So this is a table that you can have for wind speed perturbation. I mean the summarized thing. So what it shows that the vertical wind shear is a cosine perturbation. Crosswind is primarily a cosine perturbation to the tangential component. Perpendicular component is a sine perturbation. Now, once you add all these components and the contribution in for axial flow and all these things, so what we get is ut omega r minus v naught u d your cosine ut equals to u into 1 minus a minus r beta dot v naught beta u r sine psi minus u r by r cos psi. So this is what you get the velocity component, and this is what we kind of started to I mean said that for simplified thing, this is what we said the velocity component would be like this, and now we completed that derivations um, for both axial flow and tangential component, um, where we considered different effects of crosswind, yaw rate, vertical wind shear effect, and finally we get this uh, velocity components like here. So once we have this uh, axial or perpendicular component and the tangential component, then we can use them in the use them to find out aerodynamic forces and moments. So already we have found out the simplified lift force per unit length, and now we can use this simplified. So this is what can be used for design purposes. That so let's look at the aerodynamic forces and moments. So this is essentially the flapping moment due to aerodynamic forces, which is m of beta half gamma ib omega square by 3 minus b prime 4 theta p by 4 cos psi v bar theta p by 3 k nu s u bar by 4 sin psi v naught beta by 3 q bar by 4. So here this is non-dimensional inflow, which is given as u into 1 minus a by r omega. Okay. V naught var is non-dimensional cross flow, which is V naught by omega r. V bar is non-dimensional total cross flow, with V naught q d of divided by omega r. Azimuthal derivative of flap angle, which is beta dot by omega. Gamma is Lock number, which is rho Cl alpha C IB. Q bar is non-dimensional yaw rate term, which is U by omega, and U bar is non-dimensional wind mm, velocity, which is U by omega r, which is 1 by lambda. And lambda is the tip speed. So what we right now, after deriving those velocity component, axial or perpendicular component and the tangential component, we can have the flapping moment due to aerodynamic forces. So this expression looks a bit messy, but this is what you get because these are something you are trying to analyze analytically, so that you can use this for initial or preliminary design purposes. So here all this term involved non-dimensional inflow. So everything has been non-dimensionalized based on the tangential component or tangential, I mean, either r omega or in terms of omega. So all these different parameters have been clearly defined here. So all of them are non-dimensional number, whether non-dimensional inflow, non-dimensional cross flow, total cross flow, flap angle, locking number, yaw rate term, non-dimensional wind velocity. Uh, so everything kind of consider here, but this is what, so again, we will kind of derive those equations. I mean, these individual components and things like that. And I mean, we'll consider term by term and then put them back in the complete moment and then get back to this particular expression. And then later on, we'll try to see uh, different simplified solution strategy to figure out or find out the solution. So we'll now mm, start looking at how we can reach or derive this particular expression for flapping moment due to aerodynamic forces. So we'll continue that in the next session.